Okay, so this is yet another video continuing on section 3.3. It's going to have 4 panels, but no R. So one thing to observe is, though the test statistics we've been seeing so far have all dealt with means or differences of means, it doesn't have to be the case, okay? We could use the median, we could use the trim mean, by the way, pause, copy, restart. We could use the median, we could use the trim mean, etc. So for example, in that wings example, instead of our test statistic being the average number of wings consumed by the M's minus the average number of wings consumed by the W's, we could have simply used average number of wings consumed by the M's, or 15 times the average number of wings consumed by the N's. And then, if you recall, there are 15 M's, men originally, but after the permutations, let's just say they're M's. 15 times the average would be the total number of wings consumed by those 15 M's, okay? And it might not be clear why we could just use either of these two as a test statistic that's seeking to answer a question between the men versus women, but the answer is here in theorem 3.3.1, which is found on page 56. So in permutation testing, if we have 2 test statistics, T sub 1 and T sub 2, if they're related via a function, so if there's some function, little f, that sends T sub 2 to T sub 1, where that little f has to be strictly increasing, so its derivative is always positive, its graph is always heading up, and x star is any permutation resample of the data, of the original data, then both test statistics yield the exact same p-value, or 2 types of permutation testing, which we haven't talked about, but either exhaustive, in which we use all possible permutations, like with the mice and the drugs, or resampling, in which we just do like 10 to the 4th minus 1 or 10 to the 5th minus 1 random permutations, which is what we've been doing in R. Okay. All right, so as long as I can find a strictly increasing function sending one test statistic to the other, it doesn't matter which one we use. For the same question, we'll get the same approximate p-value, okay? So observe, I can build a function that sends the average of the M's to the average of the M's minus the average of the W's. Because once I know the average of the M's, all the rest of the data is W's, and I can calculate their average, right? Now, this is strictly increasing, because if I increase the value of the average number of wings consumed by the M's, well, that means I've decreased the average number of wings consumed by the W's, because I've only got the total number of wings consumed by those 30 people to deal with. So the men go up, the women go down, in which case this quantity x bar m got bigger minus x bar w got smaller. So that whole difference got larger. So if I increase the x bar m, I also increase x bar m minus xw, x bar w, okay? So that is a strictly increasing function. And obviously the function sending x bar m to 15 x bar m is also increasing. I increased x bar m, I also increased the value of x bar, 15 times x bar m, okay? All right, don't have to use this too much, but just know test statistic is not unique. There could be a lot of good ways to do a test statistic. All right. Okay, so let's talk more about some of those words, exhaustive versus resampling, that I haven't used much before, okay? So this is resampling permutation testing. This is the process that R uses, all right? Each permutation is randomly generated, okay? And this has consequences. This means that R might not use all possible permutations. In fact, oftentimes it won't, because we're only asking it to do like 10 to the 4th minus 1 or 10 to the 5th minus 1, and there might be 10 to the 8th different permutations possible, okay? So it's not exhaustive. It's not all permutations. And then since each permutation is randomly selected, it's possible that the same permutation occurs more than once in these capital N number of different permutations, okay? And that's just going to be something we deal with. So you might say, well, why don't we just have R check that it hasn't used a permutation prior? And if it has, throw that permutation out and test another one. We could, but it's computationally expensive because we'd have to store each permutation, all 10 to the fourth minus one of them, and then check each new permutation against the ones that have already occurred to make sure it hasn't already occurred. So that would just slow things down and take a lot more memory and time. Okay, so we don't do it, right? Now, good news is the more resamples we do, that's permutations that might be repeating themselves, the more accurate our p-values, okay? So it turns out that the variance in the p-values that we're going to generate via resampling is equal to the p-value times 1 minus the p-value divided by n, capital N, which is the number of permutations we do. So if we let capital N get bigger, this whole fraction starts to approach 0, and our p-values become pretty stable, okay? Which is good. By the way, pause, copy. All right. Pause. Copy. All right. So in this class, every time we learn a new test, we're going to make explicit what assumptions we had for that test, okay? So that we don't misuse them. So with the permutation test, either exhaustive, all possible permutations like the mice and the drugs, or resampling when we do like the flights or the beer wings, our samples do not have to be drawn from a normal population. And I've not mentioned that before. And the reason I'm mentioning it here is many of the tests we do will assume we're from a normal population or our population is almost normal, okay? Here, we don't have that assumption, which is good. All right. And if we happen to have two data groups like men, population of men and a population of women from which we sample, or the population of UA flights and the population of AA flights from which we sample, if the two data groups are from two different populations, well, then when we pool the data and then do a permutation of that pooled data, we should have some hopes that the two populations have roughly similar distributions when the null hypothesis is true. And remember, oftentimes our null hypothesis states that the mean of this population is the same as the mean of that population. So it's sort of the natural assumption of the null hypothesis. These two populations behave the same, okay? So we're hoping that the two populations have similar means and variances under the null hypothesis. Okay, however, it turns out that the permutation test is usually pretty good when the two populations have different distributions, unless their spreads, i.e. their variances, are significantly different, okay? So we don't have to worry about the permutation test too much, except for some aberrant examples, and I'll show you an aberrant example on the final panel for this video. Okay, so copy this down. It gets a bit small over here, but copy this down and then I'll talk us through it, okay? Okay, I have two populations here. One population follows normal distribution, mean 0, variance 10 to the 6th. The other population follows normal distribution, mean 0, variance 1. So really different spreads between A and B's populations. I'm going to grab 10 squared people, samples from population A. So there's my sample from population A. 10 to the 6 are going to be grabbed from population B. So look, the size that I grab from each population are also radically different, okay? My null hypothesis is that the mean of population A is the same as the mean of population B. Hey, that's true. And my alternate hypothesis is that they're not. And what I'm going to use as the test statistic is simply the mean of the sample from A. I'm going to do permutation testing. So remember, eventually I'm going to pool these two groups together, and then each permutation is going to say, all right, 10 squared plus 10 to the 6th people, I'm going to designate 100 of them randomly to be my new A's, and the rest are going to be my new B's, and then let's calculate that thing for my new A's. Okay, record it. Away we go. All right. So from 313, if I take the average of 100 members from A, I can calculate the variance. So I'm going to take the average of A1 up to A sub NA, that's 100, and then I'm going to divide it by 100. There's the average. With the variance, I can drag the NA out as a square, and then these A's are all independent because it's a random sample, so the variance can distribute over them. So I have the sum of the variances. I've got N sub A of these variances, which will kill off one of the N sub A's in that denominator, leaving one behind. And N sub A was 10 squared, sigma A squared was 10 to the 6th, so I get 10 to the 4th. So the variance of X bar A from the original sample is 10 to the fourth. So let's suppose we observe X bar A to be 5. That's my observed test statistic. How likely is that? Let's try and get more extreme. Let's do a one-sided p-test. What's the probability that T exceeds 5? Well, I can standardize it. I can subtract the mean of A, divide by the standard deviation of A on both sides. T minus 0 over that square root is now a standard normal distribution. And I did some work that I didn't show you, but the probability that Z is greater than or equal to 0.05 is equal to 0.48. Okay, so that's my p-value. And with a p-value of 0.48, I don't reject the null hypothesis. I say, oh, 48% chance this occurred by chance. Yeah, I'm going to stick with H naught. And even though the mean is 0, the spread is, the variance is so huge, it's not unusual that I might get an average of 5, because look how much those data points can spread about from the mean, right? Okay, well, now let's pool A and B together. So I take the 10 squared from A, the 10 to the 6 from B, put them all together, grab 100 of them, and let's look at what the variance of this test distribution is now. And I'm not going to justify this at all, but there's a formula for it, and it turns out it's approximately 101. So the variance has dropped from 10 to the fourth to about 10 squared. So the variance has really dropped. All right, so, oh, sorry, that's the variance, yep. And so the resampled T's have a variance of 101 divided by that 100. We're going to take the average of 100 of them, right? So it's going to be a variance of about 1.01 for our new test statistic in the pooled data, okay? Standard deviation is that. So let's figure out again, if I observe 5, what's the probability I get more extreme? Do my standardization, subtract the mean, divide by the standard deviation of 1.005, both sides, I get a Z value on one side. And the probability in a standard normal that Z is greater than 4.975 is, to all intents and purposes, 0, okay? P-value of 0 says this 5 could not possibly have occurred by chance. So I better reject this idea that I think the means are the same. So in this case, I would reject H0. So here's the situation where vastly different variances and vastly different sample sizes means I get vastly different answers if I just look at A versus if I pool the data and do a permutation test on the pooled data. I get vastly different outcomes for whether I accept or reject the null hypothesis. So when using permutation tests, have a pause about under H naught, under the null hypothesis, do I expect these two populations to have similar variances? And hopefully the sample sizes that I pull from each population are somewhat similar to each other, okay?